Hi. With this video, we're going to talk about what we can do to improve this general Monte Carlo simulation performance. This is really motivated by the previous calculation where we saw the coefficient of variation of our probability of failure estimate was a function of the probability of failure and the number of samples. And so the question is, what can we do to make this work better? And so the brute force way to do it is just increase the n. So the more samples we do, the better we're going to do in terms of reducing that estimator variance. So that's the easiest in concept. Could be hard for the computer though. And we may run into situations where we can't feasibly increase that further. A second strategy, which is the one we're going to talk about next, is increase the probability of failure. So if looking at that formula, the top probability of failure in the numerator doesn't really play much of a role because it's still very small. The bottom one, if I can double the probability of failure here, that has the same role as doubling the number of samples I've got. So that's an interesting strategy. And we're not going to do it by making the system less safe. That would be counter to our role as a civil engineer, right? But we're going to reformulate the problem. We're going to solve a different problem with a higher probability of failure. Okay? And then the third thing we could do that's not totally obvious in this equation, but I'll explain why it's relevant, is we can not sample independent xj. Okay. And the idea here is if I back up, when we were doing our calculations of the variance, we said that the variance of this sum here was equal to the sum of the variances, just n times the variances of the qj's. But that's true because these are independent. If I sample xj's that are not independent, and the qj's will not be independent, I can either increase or decrease this variance. So we have to be careful. We want to decrease the variance so we can decrease our estimation error. But there are some techniques that have some potential to do that. And we'll touch on this later. But specifically, we can think about Latin hypercube sampling. And another technique that's similar is called quasi Monte Carlo. So those are some ways to basically systematically sample these xj's in a way that maintains the benefit of the Monte Carlo calculation without having these independence that impacts our variance. But let's talk about the second option first, reformulating a problem. Okay. So the idea here is going to get more failures into our samples so that we can get a better statistical properties out of this. We said we were setting this up as probability of failure. We're going to integrate over all x of this, the indicator variable of g of x less than or equal to 0 times the probability density function for x, right? And that gave us the expected value of this indicator function, which was the probability of failure. What we're going to do is, so if I've got this, I'll write it up here. So we've got this PDF here. So this is the PDF for these random variables that we're interested in. And that, the distribution of the random variables and the limit state function sets our probability of failure, right? And we don't want that to go up just for ease of solving the problem. But what we're going to do is we're going to change the problem slightly. So I'm going to leave the PDF for x in here, but I'm going to multiply and divide by this case of x. So this thing here, this is going to be a new PDF that we choose. And we're going to refer to it as the sampling distribution. So the idea is we're going to define a new PDF in here and we'll plug it into the equation. And as long as I multiply and divide by it, so it's sitting down in the denominator here too, I haven't changed my calculation, right? The probability of failure will still be the same with the caveat, and we'll circle back to it, that this k of x PDF can't be 0 in the denominator, and we're going to have divide by 0 errors. But as long as it either never takes a 0 or it only takes a 0 in a place where the indicator function is also 0, we'll be okay with that. All right, so what does that buy us here? Let's go back to our expectation operator that we were talking about. This expectation operator tells us, all right, so we have this function times a PDF, right? And we had previously been using that indicator function as our function, and the true distribution f sub x of x as our PDF. So with the sampling distribution, we're going to tweak this a little bit. So for this expectation, trying to draw the parallel between this calculation and the expectation, we're going to have the sampling distribution be our PDF, and the indicator function times this ratio be our function that we're interested in. Okay. With regard to the sampling distribution k of x, we're going to compute the expectation of the indicator function times this ratio. The approach is going to be, let's generate samples of xj from the sampling distribution. That's why we call it the sampling distribution. That's where we're going to get our samples from. Then we're going to estimate the probability of failure. We're going to count up we get failure or not for each one of those samples, j equals 1 to n. And we're also going to multiply it by this ratio that's going to correct us back. This term here, we're going to call it the importance sampling weight. Mathematically, this all pencils out. It's not, inherently a better strategy, but the idea is going to be, we're going to choose the sampling distribution carefully. Specifically, we're going to choose it so we get more failures. So if we get more failures out of that sampling distribution, that's going to help with the statistical properties. And then this important sampling weight here is going to say, hold on, all those samples you generated, they were more likely under your sampling distribution. So this denominator, it was more likely that we got these kind of bad x's that caused failures under the sampling distribution than under the true distribution. So this ratio here is going to say, usually the numerator is going to be smaller than the denominator, saying that under the true distribution, the sample would have been less likely in the failures. So we're going to get these ratios that are less than 1. So we'll get more failures multiplied by a ratio less than 1, and we'll end up with kind of the same probability of failure on average. And that's the idea here. And let's try to draw a picture as well, too, to help us out. So the general scheme here would be that if I had this gray, and let's label this in. So if I had this gray PDF as my true distribution, right, and I'm going to sample proportional to the PDF, so I'll get lots of samples in here. And then occasionally I'll get a sample out in the failure domain. And I'm not getting very many of those, so I'm having this kind of numerical, the variance in the estimator problem. So the idea is, if I choose a sampling distribution that is over here, then I'm going to get lots of samples around here. And if I put it right on the boundary, I'll get half and half kind of failures and non-failures approximately. Right? So I'll get lots of failures, but then the PDF for k of x is a lot higher than the PDF for f of x for most of these samples. So I'm going to have that importance sampling weight that's going to downweight all of those failures that I saw. Okay. And that'll give me kind of a preferential result. I mentioned, though, this is not inherently a good strategy. If I picked a distribution that was like over here, that's not such a great idea. Okay. Because I'm going to generate a bunch of samples that don't cause any failures, or they're not necessarily more likely to cause failures. They could be less likely to cause failures than the original f of x distribution. And so I'm not getting a benefit there. But further, these importance sampling weights are adding some extra kind of noise into the process. And I do pay a little bit of a penalty with those importance sampling weights in terms of statistical precision. So I can get a worse performance out of an importance sampling system than I could out of a crude Monte Carlo. But if I choose the sampling distribution well, if I choose like this red distribution, I can do a pretty good job and we can get a lot better numerical performance. And so that's the idea here with this importance sampling. I think that's probably a good place to stop because we got the basic idea down. We'll follow up with some more details in the next video.